Okay, so today we're going to talk about the derivative. Some books this is 2.7 and 2.8. Some books this is 3.1 and 3.2. Just focus more on the fact that this is the derivative. We know that the average rate of change of a function on an interval, closed interval from a to b is given by f of b minus f of a all over b minus a. But we know this is just the slope of the secant line, right? And it passes through the points a f of a and b f of b, okay? So we're going to come down here. I did a little quick drawing. Okay, let's call this y equals f of x. So this is our function. Okay, and then the green line is my secant line. Okay, so we have this intersection right here. Let's call that a, and that would be the height of f of a, right? So whatever you plug in. But then we also have this other intersection over here. And what I want to do is I want to show you that this distance that we normally write, this distance from A to the next coordinate, we have a distance of h, okay? So this is actually whatever A was plus h, and that's how we could redefine our B, right? And then that means that this would be f of A plus h, okay? So if we wanted to find the slope of this secant line, we could say that m secant is equal to f of a plus h, right? Because that's my higher y coordinate, minus f of a all over b minus a. But in this case, b is a plus h minus a. So this becomes f of a plus h minus f of a all over, the a's cancel, all over h, right? So this would be our new formula based on the way I wrote it above, okay? However, what happens as I start making the distance from a to a plus h? What happens as h approaches a distance of 0? That means we're picking up the point and putting it here, picking up the point, putting it here, here, here. So eventually we're going to have this point and this point. And instead of drawing a secant line, we're going to end up drawing this tangent line, right? Because h is approaching a distance of 0. So the only way I can have h approach a distance of 0 and not actually make it to 0 is I have to bring in limits. So I could say that the slope of the tangent line, which is getting so close, the a and the next point are so close together that when you try to draw a secant line, you end up with a tangent, that this is worth the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so the slope of the tangent line, this equals the instantaneous rate of change. All right, we talked about that in, I think, 2.1 maybe. Instantaneous rate of change of a function. Okay, so this is going to end up becoming what we call our derivative. Okay, so we have the derivative of a function f of x at a point x equals a is denoted by f prime of a. So this is how you write the derivative, f prime of a, and is given by, and then here will be our formula. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. If the limit exists, and does not equal plus or minus infinity. Okay, so we don't want plus or minus infinity from these limits. That's normally bad. So something to keep in mind is that the derivative at a point x equals a is the same as the instantaneous rate of change at that point, and it's the same as the slope of the tangent line. at that point. So if somebody asks you for the instantaneous rate of change, you're finding the derivative. If somebody asks you to find the derivative, you're finding the slope of the tangent line. They're all the same thing. It's just other ways to word it, okay? So that's a big deal. So let's suppose that I say find the derivative of f of x equals 3x squared at x equals 1. So my a is 1, right? So what I'm going to do is I'm going to say f prime of 1 equals, and then I have to do f of 1 plus h, right? A plus h minus f of 1 all divided by h. So oops. Let me not forget this. I was just about to tell you guys, do not forget this. Limit as h approaches 0. Do not forget to write the limit as h approaches 0, because otherwise it's not the derivative. So we have the limit as h approaches 0. Now I'm going to actually, let me write it over here. I'm going to actually take the limit as h approaches 0, and I'm going to plug in 1 plus h into my function. So this would become 3 times 1 plus h quantity squared minus f of 1. But we know f of 1 is just going to be 3, all divided by h. So normally we like to plug our limit in right now, right? But we can't, because we would have division by 0. So we need to kind of do some cleanup like we did in the previous section. So we say the limit as h approaches 0 of 3 times 1 plus 2h plus h squared. I just FOILed that out, all over h. And then I'm going to write the limit as h approaches 0 of 3 plus 6h plus 3h squared minus 3 all over h. Now I finally see that I can clean some stuff up. This 3 and this 3 cancel. And then this has an h, this has an h, and this has an h. So I can factor h from everything. So this will become a 1, this will become a 1, and this will become h to the 1. So this becomes the limit as h approaches 0 of 6 plus 3h. Okay, now we can finally plug in. All this work was to get rid of this denominator of 0, right, of dividing by 0 when we plug the limit in. So now we just get 6. So f prime of 1 is equal to 6. And that's it. You found your slope. And this is, by the way, this is the slope of the tangent line. Okay. Now this is when you know A. Okay. So what if they ask you now, what if they say, find the equation of the tangent line? Okay. Well, in order to do that, all I have to do is I remember my old formula. It says y minus y1 equals m times x minus x1, right? So we know that x equals to 1. But if x equals 1, right, or a equals 1 or x equals 1, and we plug that into here, we're just going to get 3 times 1 squared, which is 3. So we actually have the point 1 comma 3. That's our point. So that's what we can plug in to here and here. So let's do that. So we have y minus 3 equals my slope of 6 times x minus 1. Okay, so this is the correct answer, but if the homework or the exam asks you to put it in y equals mx plus b, you just do y equals 6x minus 6 plus 3. So y equals 6x minus 3. And this would be the equation of the tangent line. 6x minus 6 plus 3, yep. So that would be the equation of the tangent line. This is only the slope of the tangent line. This is now the equation of the tangent line. Okay, so let's take a look at another one, a little bit harder one. Okay, so now let's find the derivative. So they'll say find the equation of the tangent line to the to f of x equals square root of x at 2 comma square root of 2 at that point. Okay, So the first thing they did is they tried to trick us by saying, find the equation of the tangent line, right? But that's kind of math code for first you have to find the derivatives to find the slope, and then you find the equation. So the first thing we're going to do is we're going to find f prime of 2. So we're going to do limit as h approaches 0 of 2, oops, let me write this correctly, the square root of 2 plus h minus f of a, which would be the square root of 2, all divided by h. Okay, so you guys learned something in, I think it was 2.4, maybe 2.3 or 2.4, where we were able to rationalize the numerator or the denominator by using the conjugate, and this would somehow or sometimes help us work with limits. So we, once again, we cannot plug 0 in because you would have division by 0, so we have to find another way. So I'm going to multiply by the square root of 2 plus h plus the square root of 2 all over square root of 2 plus h plus the square root of 2. So I'm going to multiply by the conjugate, and this will give me the limit as h approaches 0, and this will now become 2 plus h when you distribute. And remember, these are conjugates, so you only have to do the first term and the last term. So that would be 2 plus h minus 2. Let me see here. 2 plus h minus 2 all over h times 2 plus h square root plus square root 2. So that would then become the limit as h approaches 0 of h over, because these cancel, right? H over h times square root of 2 plus h plus square root 2. Now we see the h's will cancel. H cancels and h cancels and becomes 1. Now we can finally plug in our limit. So this will become 1 over, and if we plug a 0 right in there, that will become square root of 2 plus the square root of 2 would be 2 square roots of 2. Okay. So when we plug 2 in, we get 1 over 2 square roots of 2 as our derivative slope, or I should say our slope of our tangent line. So this, and again, once again, this is equal to m tangent. Okay. So now if they want to know the equation, well, they already gave us the point. So I'm going to come over here and I'm going to do y minus the square root of 2 equals m, which is 1 over 2 square roots of 2 times x minus 2. So once again, this is the correct answer. However, if they ask you to put it in y equals mx plus b form, then you have to do y equals x over 2 square roots of 2 minus 1 over the square root of 2 plus the square root of 2. And then you'd have to clean this up. Maybe I should have wrote this better. 1 over 2 square roots of 2 times x. Let's see here. This needs a square root of 2, square root of 2. So then we would have, if I clean this up, what would that become? Negative 1 plus 2 all over square root 2. Oops, I did it the wrong way. Sorry about that. So this would be 1 over the square root of 2 plus the square root of 2. So this guy needs to rationalize his denominator, and then I can clean them both up. So this will become minus square root 2 over 2 plus square root 2. Yeah, this is not a fun one. 2 square roots of 2x, and then this would become minus, and then we have, I'll just do plus negative square root 2 plus 2 square roots of 2 all over 2. Geez, this is terrible. So hopefully they don't make you clean this up. So this would actually be plus square root 2 over 2. Geez, I'm sure there's a better way I could have cleaned it up. For whatever reason, I just thought about it weird right now. I probably could have done it a bunch of different ways to make it better. But again, This answer would be acceptable if they do not ask for it in y equals mx plus b. If they do, then you got to do all this little extra work, okay? Because they just asked you to find the equation, and this is the equation of the tangent line. Okay, so we did our job, all right? Okay, so let's see here. So something I like to do, by the way, is I like to do like a more general form of this. I have a, so this is the derivative at a specific point. But what I like to do instead is I like to do a derivative that is the more general form of the derivative, okay? So the general form of the derivative, so meaning that it's not at any given point, you're just finding the derivative for a function. Okay, the general form of the derivative is given by, and then we have, you know what, is given by, let me see, general form of the derivative. Let's just do it this way. So this will be the derivative of a function of x is denoted by f prime of x and given by f prime of x. Notice it's not at a because they're saying you don't know the point, you're just finding the general derivative, right? The derivative for the entire function anywhere at any given point. Limit as h approaches 0 of f of x plus h minus f of x all over h. And I've also seen people use delta x and stuff like that, okay? So what we're gonna do this time is I wanna find the derivative of, so now, oops, so that's the general form. So this is very important. This is the one I use all the time. I don't normally use the a plus h one. I just use this one, and then I plug in a at the end of the problem. So if I ask you to find the derivative of s of t equals t squared plus 2t. Okay, so that means that they didn't give me a, so I just have to assume they want the general derivative. So I'm going to find s prime of t equals the limit as h approaches 0 of, now I'm going to plug in t plus h. You know, sometimes it's x plus h, or in this case, it's going to be t plus h. So I'm going to say t plus h squared plus 2 times t plus h. So all of that was just f of t plus h, okay? Minus t squared minus, oops, plus 2t, all divided by h, right? So now we're going to do the limit as h approaches 0. This will become t squared plus 2th plus h squared plus 2t plus 2h minus t squared minus 2t all over h. And in general, you guys, a lot of the numerator is going to clean up. I just FOILed this out, right? And I distributed this, and that's how I got that. So here's the negative 2t squared. Here's the negative positive t squared. Here's the negative 2t. Here's the positive 2t. So let's do a rewrite. So we end up with 2th plus h squared plus 2h all over h. We see they all have an h in common, so I'm going to factor it out. So this becomes h times 2t plus h plus 2 all over h. And that's great because now I can finally cancel my h's, right? So now I end up with the limit as h approaches 0 of 2t plus h plus 2. When I plug in 0, I get 2t plus 2. Okay, so that means then that f prime, or I'm sorry, s prime of t is equal to 2t plus 2. But what if the follow-up question is, follow-up, what if they then say, find the instantaneous velocity at t equals 3 seconds, okay? So then what you have to do is you say s prime of 3, and you say, well, that's 2 times 3 plus 2 is equal to 8. So that's my instantaneous velocity. So sometimes they give you this, but see, now that they gave me that, now that I have my derivative s prime of t, by the way, s prime of t is also known as v of t, the velocity function, okay? Because velocity itself, instantaneous velocity in this class, whenever I refer to velocity, normally I'm referring to instantaneous velocity. That is an instantaneous rate of change, which is in fact the derivative. So you can take a derivative and compare it to velocity often, unless it's specifically said otherwise. So what I just did was, now they could also ask me, what if they said, find s prime of 7? Well, then I would just do 2 times 7 plus 2, which would be 16. So that means the instantaneous rate of change at 7 seconds would be 16, okay? Or the velocity at 7 seconds would be 16. So again, I can now do any time they ask me because I have my general derivative, okay? So that's why we like to do that. Let me see here. Why don't you guys try to find it? Oops, let me give you one and you pause the video and try to do this one on your own. So find f prime of x for f of x equals 1 over x, okay? So take a minute to find this derivative real quick. Pause the video, give it a shot using the limit definition of derivative, and then come on back and see if you got it right. Okay, so hopefully you guys have already done this. So now you have f prime of x is equal to the limit as x approaches, as h approaches 0 of, and now we're going to do x plus h. So this will be 1 over x plus h minus 1 over x, right? F of x. And this is all over h. So once again, this is a problem like we did in the previous sections where you had uncommon denominators. And I told you guys the way to fix that was to make them common denominators. And then this one would be times x, and this would be times x, right? And again, it's because we can't plug in h, because if we did, we would end up with 0 over 0. So now we're going to have the limit as h approaches 0, and this will become x minus h all over x times x plus h divided by h, right? I just wrote this as division just so we can see it a little bit better. Now this will become the limit as h approaches 0 of negative h all over x times x plus h times 1 over h, because this and this cancel, right? So now we have the limit as h approaches 0. These h's cancel, and we just have plain old negative 1 over x times x plus h. But what is h approaching? H is approaching 0, so when I plug that in, I get negative 1 over x squared. And that is in fact my derivative of 1 over x. Now they can ask me, what happens when you say x is approaching 2 or x is approaching 3? Well, then I would just say f prime of 2 would be negative 1 over 2 squared, which is negative 1 over 4. If they ask me f prime of 5, I can say negative 1 over 5 squared, which is negative 1 over 25. Right? So because they, I found the general form of the derivative, I can just plug in any value they now ask me. So that's why I really like this particular question, because I can find the slope of the tangent line for any value you now give me, and I don't have to recalculate it. Okay, so that's basically, you know what, I want to do one that's basically the ways we can work with the derivatives. What I'm going to do is I'm going to end this video, and then I'll do another little short video later on about interpreting graphs of derivatives versus their original functions and stuff like that. But for now, that'll be kind of the video that covers derivatives. Okay. Thanks for watching. See you in class.